So we're looking at well-behaved preferences, namely the kinds of assumptions that we have to make, the properties that we have to impose on preferences, in addition to rationality, that are necessary in order to construct a utility function. So as it turns out, rationality is not sufficient on its own to be able to give a utility representation to rational preferences. We need other desirable properties. The first assumption is that of monotonicity, which is the idea that more is better. We say that the preference relation is strongly monotone if we look at two bundles, y and x, two commodity bundles, and y is larger than x for some commodity, at least one, but no less for all the other commodities. So for example, 2, 1, 1, 1, right? If you take the first commodity, y has more than x. If you take the second commodity, y does not have less than x. It must have at least as much as x. So if that's the case, we say that the preference relation is strongly monotone if this entails that y is strictly preferred to x. So having, for at least one commodity, just a little bit more in the bundle than another bundle, and no less for all of the other commodities, we have at least the same amount, that entails strict preference. So we disallow the possibility of indifference. Right? I am not allowed to be indifferent to any commodity in my bundle. If you give me just a little bit more and hold everything else constant, I'm going to prefer that new bundle where I've slightly increased that one commodity. Monotonicity, just regular monotonicity, T simply means that I'm allowing the possibility of indifference, so I have to have more for all the commodities in my bundle in order to strictly prefer that bundle. So if I compare y and x again, I need y to be strictly greater than x for all the commodities in y in order for me to say that y is strictly preferred to x. So to go back to my prior example, here, this first bundle, 2, 1, the first commodity does have more in y than x, but for the second commodity, I have the same amount, so it's not sufficient for me here to be able to say that y would be strictly preferred to x. Monotonicity, I need all the entries here to be greater in y than in x. So for example, if I have 2, 1, and x has 1, 0, then that's good, right? And that means that y is strictly preferred to x. One situation I haven't really discussed here, I'll write this at the top because I'm running out of space, is the idea that, hey, what can you say of two vectors if you have more for the first commodity but you have less for the second commodity? Okay, how would you be able to compare these vectors? As it turns out, you would not. You can't really say much about these two vectors, and you would not be able to say whether the first vector is preferred to the other or vice versa. Okay. Now, in most cases, a weaker assumption will actually be sufficient. I don't need to impose full monotonicity of the underlying preference relation. It is sufficient for me to have local non-satiation, which is a weaker assumption, meaning monotonicity entails local non-satiation, but the reverse is not necessarily true. Local non-satiation is the idea that thick indifference curves are ruled out, they're disallowed. So if I take a commodity bundle X, let me draw a commodity space. Here's a bundle X. Let me consider another bundle y, which is going to be identical to bundle x in terms of how much of the second commodity we have. This is commodity 1, commodity 2, but it will have slightly more of commodity 1. And slightly more here means I'm restricting myself to a very small change, which I have to draw at a large scale here so you can see what I'm doing, but this little epsilon here is just a very tiny increase in the amount of commodity 1. Well, local non-satiation simply entails that y must be strictly preferred to x. If I'm restricting myself to a very, very small change, small increment in terms of how much commodity 1 there is in the bundle, well, I will still be able to do a little bit better, and I will always prefer the bundle that contains a little bit more, right? In mathematical terms, I can say that for all commodity bundles in the space x and for all epsilon, no matter how small, so I can take this epsilon to be arbitrarily small, I will always find a y, there exists a y, another bundle, which is in this commodity space, which is such that the distance between x and y, right, this is the concept of the Euclidean distance, is smaller than epsilon, and y is strictly preferred to x. And we can see why this rules out thick indifference curves, by the way, right? Because if the indifference curve had the following shape, so let me just draw something like this, okay. All right, and it's thick, so everything in here is actually contained in my indifference curve. If that's my indifference curve, then I can see that I can find a point, namely any point inside the indifference surface here, which does contain a little bit more than bundle X of commodity 1 or commodity 2 for that matter, and that would not be strictly preferred, right? I would be indifferent between the two bundles, even though this bundle here Y does contain a little bit more of commodity 1. So that's being ruled out, okay? And the reason is, of course, that I want to be able to draw these indifference surfaces, and I want them to be lines. I don't want them to be a surface like this. I want them to be thin. By the way, it's very easy to see why monotonicity entails local non-satiation. If the preference relation is monotone, I know that if I have a little bit more of one commodity, immediately that is preferred, right? By definition, that's actually the definition of strong monotonicity. So strongly monotone or even just monotone preference relations will always automatically satisfy this test for local non-satiation by definition, because more is better, even if the more is just a tiny little bit amount.